Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to this next class on the spectrophotometric titrations, which I have initiated in the previous class itself. It's a very important component because almost all the parameters that you derive from the transition metal, coordination chemistry, complexes, etc., do go through a huge amount of spectrophotometric titrations. So here is one example where the platinum 2 complex is being oxidized to platinum 4 with the hydrogen peroxide. So again, you add your you take your platinum 2 complex, which is PtCl4 minus, add the H2O2, and this oxidation is followed as a function of time. So it's a kinetics basically. You can see on this side PtCl4 OH2 because there are 6 minus and so platinum 4 plus. So platinum 2 plus going to the platinum 4 plus. So that can be worked out in terms of your reaction kinetics. So the kinetic parameters can be derived from this absorption spectra. Let's look at another example here. This is the cyclic ligand with the 3 nitrogen containing another N3 and then another 2 sulfur. So it's basically N3S twice kind of a ligand. So this is a cyclic ligand with N3S whole twice. So it's certainly suitable for, and if you look at here, one N3 and S, N kind of thing, then you have N3S, N. Okay, so that kind of ligand. So that means one can think of visualizing one complex with the metal here, another complex of forming in the another metal ion. So this can form like the one ligand with the 2 metal ions. So the ligand and metal ion. So this has got 8 coordinating sites, as you can see here, 3 nitrogens and sulfur, another 3 nitrogens and the sulfur. So now if you titrate this with the copper BF4 twice, the copper 2 plus salt, here in this case, as you can see, and there is an increase in this charge transfer band around 320, around that, and then there is also an increase in this particular band around 270, etc. So 260. So you can follow up both of these, and then as a function of the concentration of the copper added. In the previous example, it was the time parameter. Here is the concentration parameter. You can see the rapid increase and a saturation, a rapid increase and a saturation. And if you look at the saturation point, it comes somewhere around 2. So that is what it shows, the 1:2 complex formation in these ones. Earlier in the previous class, I explained to you the 1:1 complex of this, and here I have the 1:2 complex, and I have explained the oxidation process, which you can follow by that through the kinetics, and we can see a few more examples as well. The previous example was the cyclic one, but you can also have non-cyclic or acyclic one. So this looks like a cyclic but not cyclic, it is not connected here. So this also has got 1, 2, 3, 4, 1, 2, 3, totally the 7. So these ligating centers, the 7 ligating centers are there, one extra. So this tridentate portion, another tridentate portion with a phenolic OH. Okay, so this forms a complex both with the cobalt as well as the zinc. And if you look at this, these 3 are poised for one metal, obviously these 3 are poised with another metal, and this hydroxy is poised for bridging kind of thing. You can expect that a bimetallic kind of a complex formation in this. For example, here if you take the cobalt 2 plus and keep adding cobalt 2 plus concentration, These are all at different, so you can see a band increasing here, the band decreasing, and etc. So there are one here, another here, two isobestic points which I explained to you in the previous class. So there is a complex formation, and this is with the zinc, obviously not the cobalt. So you have more greater the charge transfer here, increasing, decreasing in that, etc. So you can plot these intensities, you can again find. So both of these plots have an increase in their intensity somewhere here, and then saturates, and this value is somewhere around 2. That is the ligand, the copper 2 plus by the ligand. So we keep on adding the copper 2 plus. In this case, no, it's first one is the cobalt 2 plus, and the second one is zinc 2 plus. So this is your absorbance. So this is done for cobalt 2 plus, is also done for zinc 2 plus ion. So both are shown in this particular slide, and this is for the cobalt, this is for the zinc, and you can see this is happening at the two equivalents. So that means you can establish the complexation, and from the structure of this you can build the possible structures of that as well. Though directly this particular spectra do not imply the structure, but the structure implications can be derived from that by comparing with that, because the intensities are not so high. So that means they are forming some kind of a octahedral type of a complexes. In the octahedral complexes, obviously 3 ligand plus 1 bridge is not sufficient. That means solvent and other anions could be binding as well. So you can get some kind of a geometry related aspects, the ratio, the metal to the ligand ratio aspect, etc. If you take the individual, the final complex of this, the ligand is shown here, and the complex of the cobalt is with the blue thing, and the complex of the zinc is shown over here. It's the final complex. This is a titration, this is the absorption spectra of the final complex. That means you complete the whole titration, isolate the compound, redissolve, and look at the absorption spectrum. So this last spectrum here would match with the last spectrum over there, because the complex is completely formed. So I hope there are several demonstrations will make your understanding more stronger. So not only finding out the ratio between the metal to the ligand complexation, and by looking at the absorbance values, whether it is a tetrahedral or octahedral, other things can also be talked about. In some cases, the ligands will bind upon deprotonation. So for example, here a ligand over there, here a ligand over there, here, and this can undergo a protonation, deprotonation kind of things, and this protonation, deprotonation can be driven by changing the pH. So what you do here, you take this compound, you start varying from, you go from acid to the base direction, acid base. So this is the acid base titration. So earlier it was a metal ion concentration, but here it is a acid base titration. So as you keep starting from acid going towards the base, then you are changing the nature of the species, therefore you are changing the absorbance values, absorption spectrum itself. Now what is happening? There is as you keep going from acid towards the base, see that this band keeps rising around 550 or so, and the band around 450 starts diminishing into this. So if you can follow either this or that, and then you plot, you can see a very nice sigmoidal plot. So you get a very nice sigmoidal in this case. So the sigmoidal plot, so if you take the derivative of this, then you can make. So this is, you can have H plus concentration, you can have absorbance. So from this you can get the pKa value. So you can get the pKa of this for this. Okay. So if there are multiple pKas, you might get multiple sigmoidal plots. So example is in the next one here on the right side in the same slide here. You have one phosphate over there, another phosphate over here, and another phosphate. You can get even 3, but you get clearly only 2, but not the 3 in this particular case. So you can see in this is also done. You take this particular ligand, start going from acid towards the base, kind of acid base titration. It's a little broad thing. So that means one of the pK is happening here without not sharp, then there is another broad feature between 6 and 8, and there is another one between 9 to 11. So therefore, one pKa over here, the other pKa is here, and then one more in the acidic region, which is not very well resolved. That's what generally you find. So you can get multiple pKa values if there is a multiple protonation deprotonation centers in a given molecule. So here you are not changing any metal ion, nothing is added, only the changing the medium pH of that medium. So this is referred as L3 as a function of pH, and then the B is variation of absorbance at the 256 nanometer, this one, and that is what is plotted, and these are the parameters which are used, concentrations and other things. I hope now you got from the several titrations that I have demonstrated so far, you would have got it. Let us look at maybe one more with the where you can have a protonation deprotonation as you go from acidic to the basic, which would lead to different kinds of the speciation possibility. So the speciation possibility can also be seen from the absorption spectrum. That is, you can have one protonated, two protonated, etc., and then those kind of corresponding species as well. Okay, so that let us see the example over here. This is the main molecule referred as a L, and then this can form one protonation here at this pyridyl group. It's called HL plus. This can also get another protonation here, one here, one here. That will be two protonation, diprotonation. So the L, then HL, then H2L2 plus. So there is a species. So this is one, a neutral species, is a monocationic species, the dicationic species. So obviously their absorption band positions, intensities will vary. So as you keep varying the spectra, you can see that things going in this direction, things going in that direction, etc., as I have explained earlier. So at different values of it. For example, at an acidic pH, there is a very high value at this 350, 360. As you increase the pH, you can go down, it is going down, the absorbance is going down, you are increasing the pH only, so that absorbance goes and completely diminishes. So at the basic, this is completely species is lost its proton kind of thing. On the other hand, this particular band at a highly acidic, it goes to here, it goes here further and then up. So one is going down, other is going up. So using this one, and you can see there are some isobestic kind of regions. So you have the multiple protonation, deprotonation kind of thing situation is happening. So you can derive all that. So in the earlier example, I told you for such kind of things, plotting the absorbance versus the pH will give you pKa. But now plotting the wavelength versus the absorbance converted into epsilon value. So the absorbance is converted into epsilon value. How? Because we know the species of this, so its epsilon is known, H2L2 plus epsilon is known, the L epsilon is known. So since we know the epsilons of these, then therefore from the concentrations you can convert into epsilon and then plot here. So not directly from the spectrum gives absorbance and the position, then divide with the corresponding value, then you get your epsilon. So this peak is for the HL plus, the H2L2 L2 plus and then L. So you can see the level of the species of L keep increasing to H2L and then keep increasing to the HL plus, all of these. So if you use a pH titration thing, like for L you have only one. Then if you take the HL, you can see this is the kind of spectrum. The H2L2 plus, you can see that. So at very highly acidic, only you will find H2L plus. Somewhat little less acidic, like 4, 5, you will start seeing HL plus, and 6, 7 beyond, you will see only L. So the other way. So neutral, you will see L. Little bit more acidic, you will see HL plus. Much more acidic, you will see H2L2 plus. So you can go from this to this. That means basic to the acidic, or you go from acidic to the basic. There is nothing the magic, so you need to use these terms to get this. So that means absorption spectra are sufficient enough to work out the species distribution. Here from the area you can talk about the species distribution at a given pH. If it is a very low pH like acidic pH like pH 2, it will be mostly HL2 plus. If it is somewhere 4 to 5, it will be somewhat less acidic, then it will be HL plus. If it is beyond 5 or 6 or neutral, then there is very little of HL plus, very little, much less of H2L plus, and it is mainly L. So I hope this way of understanding the spectrum to the species and species to the spectrum will help you in understanding such kind of a titrations. I hope this is clear. Not only that way, you can also do this in presence of the metal ion as well. You can take this particular ligand which I have talked on the previous slide, and now you can add the metal ion, like for example in this case iron 3 plus at a specific ratio. Here this titration is done, the iron 3 plus to L is 1:2 ratio, because there are primarily acts as a tridentate. So therefore the iron 3 plus favors more of a octahedral, so therefore you can expect the two ligands to be binding. So you take 1:2 ratio and then do pH variation titration. So the pH variation titration. So what all these are going from acidic towards the basic. So here it's completely basic, you are not going here. And then you have some 7 and 9, okay, over there. So that values can be plotted, and then you see the absorbance at 420 nanometer. Here this is plotted here as a function of pH. So you can see this particular complex is between 3 and 8. This complex is stable. So you can get the stability of the complex too. So more or less stable, of course. So between 3 or 3.5 up to about 8.5 pH range you can make. So that means in future, if one would like to do any kind of a studies using this complex, any catalysis, any transformation reaction, etc., they can do that reaction within that range, because beyond that it will break down into the ligand and the metal ion. But during that pH range it does not break down. Okay, so similar kind of things can be done even for the copper. It's done reactions here. So you can see copper with the L, copper with the L2 plus, copper with the HL. So all of these complexes speciation with the copper. So here it is done with the copper as 1:1 at different pH, and the calculated spectra were put here, and therefore you can see the speciation. So how much is coming from the copper L, how much is coming from the copper L2 plus, how much is coming from the copper HL3 plus. So all of these can be identified from this, the kind of a titration that is carried out between the ligand plus the metal added in a particular ratio, and then the pH is being changed. Now we have seen large number of spectrophotometric titrations. A simple ligand to metal variation, ligand to some two components added time variation, or pH variation. So variety of these things you can derive almost all the parameters from that. Okay, so that's quite a much on the absorption spectral titrations, and let us look at some situations where the coordination complexes are a part of the proteins. So they are the protein. So this is the metalloproteins or metalloenzymes. So in this, what happens, the metal coordination sphere is present in the protein, and that is what is basically referred as the metalloprotein or metalloenzyme when it does the reaction basically. Now take one example, the iron rubredoxin. You don't need to know more details of that. If you are interested, you can easily Google it and then find out. It's a rubredoxin protein, is an iron sulfur protein, and where the iron is bonded by this 4 cysteine moieties. And then the absorption spectrum has a strong charge transfer. The charge transfer can come from the sulfur to the iron, and these are what is coming over here. Now what is happening is this charge transfer is coming from the cysteine. Now if you take to confirm that it is coming from the cysteine, and the cysteine is bonded here. Now let us take this in this protein, in this enzyme. This is a protein structure. You have a cysteine binding, So this is the cysteine 42, and now if I transform this into alanine 42 and then iron, if I bind this one, obviously of course this is bound through other things as well. Okay, now this should not have, because alanine has got the methyl side chain, should not bind at all, and the cysteine has got the SH CH2SH side chain. So this should bind, and that's what is binding, and that will give the charge transfer between the sulfur and iron, whereas here it is a methyl group, does not bind to the iron, therefore does not make any charge transfer. So you can see these charge transfer bands which are present in that have been diminished. Not 100%. Reason is because there are other cysteine groups are still there. So therefore certain amount of charge transfer is still there. If it is only one and if you are replacing one, it should have been 100%. But there are 4 such cysteines are there, and you have replaced only one cysteine by an alanine. So that means in an enzyme, when you do some kind of a replacement of one of the amino acid by a different one, you can easily make out. So in other words, in the coordination complex, if one of the ligand is changed, here the cysteine is replaced by alanine. Still you can see the difference in the absorption spectrum. Look at another example of this using a different metal center. The original metal centers are iron in the rubidoxin, but iron can also be replaced by the copper. So you take the rubidoxin protein from the plant source into a test tube, replace the iron by copper. That is done. You don't need to worry how it is done, etc. There are methods by which one can do, and then let's say assume that people have done. If they have done that, you can see that the absorption spectrum comes to this. So it has a different kind, a huge absorbance in the range of 700 to 800. This is an expanded one, this is the original spectrum. Now if you compare this spectrum with the original iron one, it's a huge difference. So you have absorbance in 700 to 800 besides your 4 to 500. So here you have 4 to 600, and so therefore that can establish the replacement of the iron ion by the copper. It's completely replacement of the iron by the copper in this particular case. Now in this case also, if I replace the 42nd cysteine, C stands for cysteine, 42nd is the 42nd amino acid, A is for alanine, the absorption band is completely collapsed because you are changing only one, but there is still some more cysteines are there. That is why you found this, otherwise you would not have found even that band as well. And this also has been diminished. So this region is diminished, this region is more or less diminished. If you have replaced all the 4 cysteines which are present in the original protein, you would have seen a flat line here is a completely flat line, but it is not completely flat line because you removed only one of them. So I hope this you can see that variety of changes these are reflected in the absorption spectrum, and you can use them as well. Okay, so far we have seen examples from the direction coming up from the coordination complexes. Let us look at some examples in the nanomaterial side. So for example, the silver nanoparticles can be prepared in a variety of shapes, sizes, etc. So these can also be studied by UV visible absorption spectrum. So what will happen? Suppose you have different kinds of these let's say silver nanoparticles. As I said, they can be in different shapes, sizes, etc. Let's take the spherical itself. So one so bigger, etc. And then other kind of shapes that will come in a while. So what happens in this is you can use the UV visible absorption spectrum in this to explain a phenomena called surface Plasmon resonance. What does that mean? So you have these particles, the particles will have the electrons which are in the surface part of it. So the metal surface part of the electrons which are there, the conducting kind of electrons, when you shine light on that, so when you shine light on that, what will happen? These electrons will collectively oscillate. When they collectively oscillate, you get an absorbance signal out of that, and that is the signal which is referred as the surface Plasmon resonance in very simple terms. So if you go to physics, they will explain you full details of all of these, and this the band that comes out of this has a characteristic dependence on the size, on the shape, all of these are there. Now you can see this example here. These nanoparticles were prepared by certain kind of a method with the different ones like 10 nanometer, 20 nanometer, 30 nanometer, 40 up to about 100. So the absorption spectrum was measured for each of these. For each of these, color code is given, the black, the red, the blue, etc. You can see it's going from here to there to there to there to there, and up to here. What you see, this peak position is changing, the peak width is changing, the peak is becoming very broad, and the peak is becoming very asymmetric. There are so many parameters. So the peak position is shifting, the peaks are broadened a bit, the sharpened became broadened, from the sharpened ones to broadened, the spectra became skewed. Here you see 101, there is one, it's almost split into two parts. So there is one band here, there is another band here. If you go to this one, which is 80 nanometers here, so the strong of this and a little bit weak of this. And if you go to this one, which is around 70 nanometer, you can clearly see this band, clearly see that. That means you have at least minimum two different types of shapes of sizes of these nanoparticles are present in those. So here also you can start seeing there is a little bend here and then is another. So one coming from this region around 400, other coming from above the 550. So that's how so there is a smaller, and as you go increase, the shapes are also affected. They're not exactly 100 nanometer is not exactly the 100 nanometer 100% of the particles. Some of the particles may have a few other sizes also, because when you prepare in bulk you have those things. So that's what you are seeing basically. So it has at least two distinct kind of levels of particle sizes here. So one is giving the surface plasmon resonance absorption signal around 410 nanometer. Other one is giving around 510, 520 nanometer, you can see. So you can very well identify the shape, size, sometimes even some kind of a structural features or symmetry features can be. So it also depends on the refractive index of this, because you are looking at the plasmon resonance at the surface level of this. Okay, one another example here. These are again silver nanoparticles, but in the shape of plates. So in the plate with the triangular plates. So what are the dimensions can changes? You can do the thickness. So you can change the thickness of these plates, and that will change the absorbance basically, because your surface plasmon resonance coming from different orientations of these would help in differentiating their thickness, etc. So if you look at different thickness based solutions, you can see one with this purplish or reddish kind of color to the bluish, somewhat less bluish to the greenish, there's darker greenish. If you look at their absorption spectrum, you would see something around 550, another around 650, 750, 850, 950. This means you can tune the surface plasmon resonance absorbance as you keep tuning the size or the thick size of these platelets or this. And from chemical methods you can always work out. So you're going from somewhere visible region to almost the near IR. You can look into a variety of domains of applications of this. Okay, so there are things of that kind. So we can keep looking at some more examples in the nano composite in the next class, and then we will also look at how whether we understood this subject in depth or not by having some kind of a practice session, queries, examples associated with that, which I will take up in the next class. Thank you very much.